In this lesson, we'll do an introduction to average rate of change, and we'll start with a warm-up example here. So consider the graph on the right here, which describes Paul's 10-second run, not a very long run. Now, as you can see, we have a bunch of straight line segments for this displacement time graph, which means we don't have a very realistic graph here. There's no speeding up or slowing down happening. But anyway, it's good enough to serve our purpose here. So let's start by looking at each part of his little journey separately here, starting with the interval from 0 seconds to 4 seconds. So what's happening here? Well, Paul's moving at a constant velocity or a constant rate in the positive direction. Now, how do we know that it's a constant rate for this part of the journey? Well, we have a straight line. That is, the displacement is always changing at the same rate. The slope of this line never changes for the first 4 seconds here. Now, if we wanted to actually find his velocity, we're going to get a positive value because this is a line segment with a positive slope. And we could calculate the velocity by finding the change in displacement and dividing it by the change in time for any 2 points on this line. So for example, we could take the first point and the last point of this line segment. That gives us a run of 4 and a rise of 8. And if we do a rise divided by run, that is the slope, and it's also our velocity, which is going to give us 2 meters per second. All right, now let's look at the next part of the journey here from 4 seconds to 8 seconds. That's right up here. And he's not moving. How do we know that? Well, we have a flat line, a horizontal line, which means for those 4 seconds, his displacement is not changing. And if his displacement's not changing, he's not moving. We could calculate the slope if we wanted to. We'd have a run of 4 and a rise of 0 because this line, from the beginning to the end, for example, does not go up or down. So our rise over run would give us 0 divided by 4. That's our change in displacement divided by our change in time. And that, of course, is 0 meters per second. Lastly, let's look at the interval from 8 seconds to 10 seconds. He's moving at a constant rate in the negative direction. Now, why is this the negative direction? Because this line segment has a negative slope. Our rise is -8. Our run is 2. And -8 divided by 2 gives us a velocity or a slope, you can think of it that way, as -4 meters per second. All right, moving on. We need to talk about the fact that there are 2 different types of velocity. And the first of these is called average velocity. Now, what is average velocity? Well, it refers to the velocity of an object over some time interval. So whenever we talk about average velocity, which we will in detail momentarily, we're talking about a rate of change, that is velocity, over some time interval. That is different than what we call instantaneous velocity. Now, instantaneous velocity refers to the velocity of an object at a particular moment in time. And I always like to think of instantaneous velocity as, if I'm driving down the highway, for example, and somebody beside me in the passenger seat says, "What's your velocity right now?" That would be the value that I read off of my speedometer at that instant. I could look at that speedometer and say 100 kilometers per hour heading westward. Well, that is my velocity at that instant, 100 kilometers per hour in some particular direction. Okay, so here's an example. Let's say we have a friend named Zoe. She's a reckless driver, and she's driving to visit her friend Deirdre. Now, at the beginning of her journey, she reset her car's trip odometer. That's just the little reading that we read to see how far we've driven from when we reset it to any point in time after that. And after exactly 3 hours, she looks at her speedometer, which is shown on the right. And the question here is, what is her instantaneous velocity at 3 hours? Well, that's like right now, at that instant, at 3 hours. Well, if we look at that speedometer, we can see that right now, she's doing 121 kilometers per hour. In some direction, we'll say it's the positive direction. So that is her instantaneous velocity, 121 kilometers per hour in the positive direction. Now, we could also ask, what is Zoe's average velocity over the first 3 hours of her trip? Now, the first 3 hours of her trip, that's a time interval. We want to find her average velocity. Well, what we need to do to find this value is take how far she's driven and divide it by how long she's driven for. Now, how far has she driven? Well, we can look at the trip odometer here. This is what she reset to 0 before she started driving. And we know that 3 hours has passed. So if we take that 468.6 kilometers and divide it by 3 hours, we get an average velocity of 156.2 kilometers per hour. And that's once again what we're going to say is in the positive direction because it's a positive value. All right. Now, this brings up a neat kind of question. Does this result imply that Zoe actually drove at a speed of 156.2 kilometers per hour at some point in her journey? And it actually does. She cannot have an average velocity of 156.2 kilometers per hour if she didn't actually drive at that speed at some point in her journey. And I'll let you think about a little bit more around why that is. It's actually related to a theorem in calculus called the mean value theorem. Perhaps you'll look at that one day. Okay, but let's move on for now. Let's go back to Paul's run here. Remember this graph, this unrealistic graph that we had. Now, when we calculated the velocities for Paul's run, the question is, were we calculating average velocities or instantaneous velocities? And the answer here is actually both. Now, why is that? Well, it's really because we're dealing with straight lines here. And when you're dealing with straight lines, average velocity and instantaneous velocity are the same thing at any particular point on the line or over any interval on the line. Now, here's an example to show you why. If we look at the first 4 seconds, notice that we have an average velocity of 2 meters per second. You can pick any 2 points on that line and take the displacement, the change in displacement, divide it by the change in time, and you're going to get 2 meters per second. But at any given moment during those first 4 seconds, if we asked how fast is Paul moving, what is his velocity, it's also 2 meters per second because he was always moving at 2 meters per second in that interval. So when we have straight lines, average velocity and instantaneous velocity end up being the same value. But what if the velocity is not constant? This is where things get a little more interesting. If we have a curved displacement time graph, it indicates that the velocity is gradually changing. We're speeding up or kind of slowing down. So how do you find the average velocity when the graph is not a straight line? Well, let's take an example here. We have a function that's shown on the right here, and we're going to determine the average velocity over the first 5 seconds. So how do we do that? Well, we're looking at the first 5 seconds here. So let's plot the 2 relevant points on the graph. The first of which is at 0. Remember, we're looking at the first 5 seconds. So we'll plot a point right there at 0. And the other one is at 5 seconds. So we'll plot that point up here. That's the point 514. And if we want to find the average velocity over that first 5 seconds, we're going to draw a straight line through those 2 points. Now, this straight line that I've just drawn there has a special name. We call it a secant line. Okay, it's that line going through 2 points on our curve there, and we'll calculate the slope of that secant. What we get for that slope is the average velocity. So how do we calculate the slope of that? Well, the same way we calculate the slope of any straight line, we divide our rise by our run. In this case, we're taking the change in displacement, that's our rise, and dividing it by the change in time, that's our run. Sometimes we think of this as y2 minus y1 over x2 minus x1. If you look at it that way, this should make perfect sense. 14 minus 0, that's your second y value minus your first y value, divided by 5 minus 0, which is your second x value minus your first x value. That gives us 14 divided by 5, which is 2.8 meters per second. That is the average velocity. Now, let's think about what that actually means. What that means is that if we were to make this journey from here to here in that same amount of time, so 5 seconds, but if we were to do it at a constant rate instead of a rate that is changing here, that rate would be 2.8 meters per second. So it's essentially saying if we took that same amount of time to make this journey at a constant rate, what would that rate be? 2.8 meters per second. That is the average velocity. Notice that initially here on our graph here, we're not moving at a constant rate. Because we start steep and then go less steep and less steep and less steep, motion is actually slowing down here. But if we were to do that at a constant rate, it would be 2.8 meters per second, and that's what average velocity is. In general, that's what average rate of change is. And we're using the word velocity here because we have a nice word for when we talk about the rate of change of displacement. Now, we don't always have a nice word like that, but these same ideas apply when we're not talking about the rate of change of displacement. And there you go.